This is a guide to the specialized hardware that makes industrial artificial intelligence possible. Understanding this hardware is critical for any business leader looking to stay competitive. Manufacturing logistics energy. This change is being driven by data and the intelligence we can extract from it. Sophisticated software, brilliant algorithms, robust physical equipment designed to operate in the toughest environments imaginable. This hardware is the unsung hero: smart factories, intelligent supply chains. The reason this topic matters so much right now is one of simple economics and survival. We are standing at a pivotal moment in industrial history. Adoption of AI is no longer a luxury, but a necessity. Efficiency, safety, quality. Those that do not risk being left behind in a marketplace that is becoming increasingly unforgiving. The hardware is the entry ticket. It is the tangible investment that unlocks the potential of AI, predictive maintenance, automated quality control. Consider a modern automotive plant, a place of constant motion and immense complexity. Robots welding car frames with precision. Conveyor belts move parts seamlessly. Thousands of components come together to create a finished vehicle. Now, imagine layering AI onto this process. Cameras that can spot a microscopic paint defect invisible to the human eye. Sensors that can hear the subtle change in a machine's hum that signals an impending failure. This is not science fiction. It is happening today. Heat vibration, dust processing vast amounts of data in real time. In this discussion, we will demystify the world of industrial AI hardware. We will provide clear, simple answers to the essential questions. What exactly is it? What are the key components you need to know about? How do they work together to create value? We will cut through the technical jargon and focus on what truly matters for business leaders, engineers, plant managers. Make informed decisions. Ask the right questions. Confidently navigate the journey of integrating AI into your own industrial operations. Be prepared for the next wave of innovation. Industrial AI hardware is the collection of physical electronic devices specifically designed to gather data and run AI programs within an industrial setting. Think of it as the nervous system and brain of a smart factory. Unlike the computer on your desk or phone in your pocket, it is built for a much harsher world. Extreme temperatures, constant vibrations, humidity, dust, electrical interference. Its primary job is to be the reliable bridge between machines and AI, enabling real-time analysis and automated decisions right on the production line. The core components form a logical chain from data collection to intelligent action. Sensors, the digital eyes and ears, temperature, vibration, images. Data flows to edge devices, industrial PCs and rugged computers performing initial processing. For heavier tasks, GPUs, AI accelerators, the powerhouses for heavy computational lifting. Networking hardware connects everything. Rugged enclosures protect the electronics. Each piece plays a distinct, vital role. Sensors convert physical phenomena into electrical signals. Edge devices sit near the source and act as a first filter. They run simpler AI models, make quick local decisions to reduce data sent over the network. Industrial PCs or servers with high-end GPUs handle complex, large-scale models. Networking hardware ensures fast, reliable communication for time-sensitive ops. To illustrate, imagine an automated quality inspection on a bottling line. High-speed cameras capture every bottle, images sent to an edge device, AI checks for defects, simple rejects handled locally, unusual cases escalated to a central server for deeper analysis. Sensors are where the journey from the physical to the digital world begins. They are the sensory organs of your industrial AI system. The variety is immense. Vision sensors, industrial cameras, are used for quality control, checking for defects, reading barcodes, guiding robots. Acoustic sensors listen to machine sounds, using AI to detect subtle changes that indicate developing faults. Vibration sensors feel for tremors that signal wear and tear. The choice of sensor is dictated by the problem you want to solve. Once the sensor captures data, an image, a sound wave, a temperature reading, that information needs to go somewhere. This is where edge devices come into play. Placing a small, powerful computer next to the sensor has key advantages. The most important is speed. By processing locally, the system can decide almost instantaneously. Critical for emergency stops or rejecting a defective product on a high-speed line. There is simply no time to wait on distant cloud round trips. Edge computing reduces network load dramatically. Streaming all video 24/7 is expensive and bandwidth heavy. Instead, analyze in real time and send only important information, a small alert message, and a single image rather than the full stream. Sensor provides raw perception. Edge provides immediate, local intelligence. A decentralized, responsive system. Faster reaction times, enhanced data privacy, and continued function even if the central link is lost. A cornerstone of modern industrial AI architecture. While edge devices handle quick, local tasks, the most complex AI models need much more computational power. High-performance processors, GPUs, and other AI accelerators. Think, a reflex action versus deep, conscious thought. Edge handles the reflex. Central processors handle the deep thought. Root cause analysis and prevention. These processors let AI learn from vast datasets and detect complex patterns. GPUs are the de facto standard, with thousands of small cores ideal for deep learning math. A CPU might take weeks. A GPU cluster can finish in hours or days, making industrial AI practical. Deployment options: on-prem, rugged server-grade industrial PCs near the action, or cloud, renting scalable GPU power from major providers. Cloud needs stable, high-bandwidth links. Choice depends on performance metrics, latency, throughput, power consumption, and reliability with maintenance and redundancy plans. Use case 1, predictive maintenance. Unexpected failures can halt production, costing hundreds of thousands per hour. Vibration, acoustic, thermal sensors feed an edge device for immediate alerts. Pre-processed data streams to a central server for trend analysis. The central model correlates slowly increasing vibration with a slight temperature rise, predicting bearing failure in 72 hours. The system issues a targeted work order, avoiding unplanned downtime. Use case 2, automated visual inspection. A high-res, high-speed camera feeds a GPU-powered IPC trained on millions of examples to detect chips, cracks, discoloration in fractions of a second. Upon detection, a precise actuator removes the defect instantly. Hardware and software together deliver massive value. Implementing an industrial AI hardware solution is a systematic process. It's not plug-and-play. Begin with a thorough site survey and requirements analysis. Understand the physical environment, existing infrastructure, and the specific problem to solve. Assess ambient temperature, dust and moisture, available power sources, and network capabilities. Define precise project goals. Choose sensors, edge devices, industrial PCs, and networking. Balance ruggedness, performance, latency, throughput, and budget. Architect detailed connections, installation points, and data flow. Integration, mount enclosures, run power and network cabling, install cameras, sensors, and computers with minimal operational disruption. Install operating systems, drivers, and deploy AI applications, turning boxes and wires into a cohesive unit. Rigorously test end-to-end. Thousands of known good-bad parts for visual inspection. Simulate faults for predictive maintenance to confirm alert paths. After deployment, maintain hardware health, perform periodic cleaning, and plan lifecycle component replacement. Overcoming the hurdles, common challenges in industrial AI. Factories are hot, dirty, full of heavy vibrating machinery and electromagnetic interference. Consumer gear fails fast. Industrial hardware mitigates risk, fanless cooling, IP-rated enclosures, EMI, RFI shielding. Safety and high availability are paramount. Failures can cause dangerous malfunctions or catastrophic downtime. Build redundancy, backup power, duplicate servers, certified hardware. Machines last decades. Compute evolves fast. Design modularly for easier upgrades. Scale across lines and sites with architectures that grow cost-effectively. Secure every device. Strong authentication, encryption, and segmented networks. Security is not optional. It's essential to protect critical industrial operations. In summary, understanding the hardware that powers AI is no longer optional for industrial leaders. It is fundamental to future success. This is not just tougher office gear, but a specialized ecosystem built for factory demands. From sensors that gather data to powerful processors that analyze it. Each piece turns AI from concept into a practical tool for improving efficiency, quality, and safety. Implementation needs careful planning, from site survey to long-term maintenance, and awareness of challenges. 3 takeaways. 1. Industrial AI hardware is engineered for harsh environments. 2. Success is an integrated chain. Sensors, edge devices, powerful processors, robust networking, all in unison. 3. Treat deployment as a holistic strategy considering environment, safety, lifecycle, and security from day one. The journey can seem daunting, but the rewards in productivity, reduced waste, and safety are too significant to ignore. The technology is mature, use cases proven, and the path well understood. The question is not if, but when and how. The hardware is the tangible starting point, the physical foundation of your future smart factory. Identify a high-impact problem. Engage a qualified integrator or consultant. Run a pilot, prove value, then scale, and build the intelligent, resilient, and competitive industrial operation of tomorrow.